we are discussing the Kuwait flows, another problem, which is flow of a thin film of oil along a infinite plate. And so we have sort of described the problem, enumerated the conditions that are being imposed, and now we try to go for the solution. For solution, we need to determine the velocity and the pressure profile starting from continuity equation as well as the Navier-Stokes equation. We obtain these values just as we obtained them in the first two problem of Kuwait flow that we considered when we were considering the flow between two infinite plates. One of those problems, there was no external pressure. In another problem, there was some pressure gradient. And this is a third case in which there is a flow of oil but with no external pressure. So the procedure will remain the same. The conditions are more or less we have already listed out, and therefore now we observe that there is no slip at the wall. So no slip condition means that due to viscosity, the fluid that is moving is sticking to the wall. So if the fluid is sticking to the wall, to the boundary, then at that point there will be no movement, there will be no motion. And if there will be no motion, the velocity component at that point will all be zero. There is no motion. And this is because of no slip condition and because of the viscosity of the oil that exists. At the free surface, when x is equal to h, the value of the shear is so small that it can easily be neglected and we take it to be zero. So when x is equal to h, partial derivative of w with respect to x is zero. Similarly, we write down the values from the continuity equation as we did before. You will remember that when we are writing dv equal to 0, expanding it du by dx, dv by dy and so on, and dw by dz, then we get nothing from here and nothing from here. The only term that we obtain is from this part. And if u is only a function of x and does not depend on any other thing, then this partial derivative, du partial derivative, becomes a total derivative, and we write it as du by dx. As I am sure you must be familiar as it happens in normally the calculus in differentiation. So we look at the same thing and we try to, from the continuity equation, these are the values that we obtain. We have nothing from coming in. This is equal to 0. So is this. And if we have dw by dz is equal to 0, then this is the only non-zero term that is appearing. And from this, we follow that w is equal to w of x only. That is for this problem which we are considering. And the only non-zero term that is left from continuity equation. Then we come to the x component, x and y component, and then z components of momentum equation, and that is the Navier-Stokes equations parts that are there. So the z momentum equation, in which the gravity is playing a role, gives us finally d2w by dx2 equal to 0. We have already just observed this thing, that if u is a function of x only, then du by dx becomes equal to du by dx, the total derivative. So if we replace u by w, then the same term will become w, as you see here. So the partial differentiation of w with respect to x being shown as total derivative, because w does not depend on any other thing. So this is what we will get, and therefore For looking of the solution, we have to integrate this equation.